taking green chemistry to Ethiopia. In case you're not good at geography, Ethiopia is in Africa, and it's this part of Africa here on the east side. And one of the things that's important is it's a very large country, and it is completely cut off from the sea. You can see there's yellow all the way round it. So it's a landlocked country. And for the last 10 years or so, I and my colleagues have been promoting green chemistry in Ethiopia. Here you can see there's a picture of 2007 where we had a green chemistry workshop in a city called Jimma, which is the center of the coffee growing region of Ethiopia. And this is our bus. And I did not have the courage to ask this woman if she knew what green chemistry was. But you can see we're interesting people in green chemistry. And then in 2010, all my dreams came true, and the Royal Society of Chemistry held its first Pan-African meeting on green chemistry in Addis Ababa, and green chemists from all over the world came to Ethiopia to talk about how green chemistry could help a developing country like Ethiopia. So the question is, how can you actually do green chemistry that might help a country like Ethiopia? And one of the tourist slogans for Ethiopia is that they have 13 months of sunshine. This is a true statement, because Ethiopia has a strange calendar that has 13 months in the year rather than 12. And so the thing that struck me and my colleague Mike George was that because they have so much sunshine, that an obvious thing to try is photochemistry. And one of the well-known chemical reactions using light is so-called photocatalysis. And this was pioneered by a German chemist called Schenck. This is a picture of Schenck in 1947 in his German summer outfit. And after the Second World War in 1947, Germany was a very substantially ruined country, and they needed this material here called ascaridole, which in those days was used as a treatment for people suffering from worms. And you can make this by reaction of so-called singlet oxygen. This is reactive oxygen that can be produced by light from this molecule here called alpha-terpinine. And here's Schenck on the roof of his lab with reactors doing this reaction. And he used as the catalyst spinach leaves. You know, spinach is the vegetable that people don't like. But he used spinach leaves, but the real problem is the solvent of the reaction that he used, which was carbon tetrachloride, which is now considered a very toxic solvent. So we wondered whether we could do these reactions, but using supercritical CO2. Mixes easy with oxygen, it doesn't burn. You have fire extinguishers with CO2. You don't seem to have a fire extinguisher in here. You should do, you know. So we did this experiment, and we found out that it really worked in CO2, and the reaction actually went faster in CO2 than it did in carbon tetrachloride. The problem was that we'd done the reaction on a very small scale. This is my colleague, Rich Bourne, who's now a lecturer in University of Leeds. And we used a little cell like this, which produced in it about 30 microliters. You can see it here in a tube. And this is an English 2p coin. I'm sorry, I don't have any English money with me, nor Hong Kong, but 2p coin is about this size and is worth almost nothing. But just to give you a scale. So we really wanted to try and make the things on a bigger scale. And the problem is that if you're working under high pressure, if you just try and make a bigger and bigger vessel, it becomes more and more expensive. Big vessels are very expensive for high pressure. So we decided to do the reaction continuously using a transparent tube, high pressure tube, so material could flow through it, and to put on either side light emitting diodes. You're probably familiar with LEDs. These are what you get in small torches. I won't shine it at you. You won't see the rest of the slides because it's bright, but you can see it here from me. And we used LEDs of the sort that you get in the headlights of Audi cars. You know, these expensive Audi cars. But fortunately, you can buy the LED without the car. So it's, so we had the LEDs, and here you can see the reactor running. And these things look like the teeth of comb are actually heat sinks to remove the heat generated by the electricity going through the LEDs. And the red light was just put there to make a nice photograph. And so we scaled up this reaction. So in 8 hours, we made 96 milliliters of ascaridole. And 96 milliliters may not seem very much, but this is about 1/10 of the amount you would need if you were testing this material as a drug in the first stage of clinical trials. The red color is due to the photocatalyst. But the other thing is, when we made this, we were really excited, and then suddenly we got quite frightened because ascaridole is explosive compound. And so this is quite a seriously large amount of material. And so we got quite worried. But then we found a student who wanted to use it in his project, and we got rid of it. So that was... So more recently, so last year, we took the idea that was pioneered or invented by István Horváth of the so-called fluorous biphasic catalysis, so that we could recycle our catalyst round and round and round without needing to put in more catalyst each time. And I won't go through all the details, but if anybody's interested, I would be happy to talk all afternoon about this. But this was published last year in ChemCom. It's the work of students Jess Hall and Han Shui. And we can compare the efficiency of our reactor, what chemical engineers call space-time yield, which is the amount of material you can make per unit volume in unit time. And a conventional reactor has, in these units, somewhere between 0.1 and 0.5, and ours is about 70 times, has about 70, so it's nearly somewhere between 300 and 700 times better than this. I'm sorry, 150 times and 700 times better. And so now we come back to the relevance to Ethiopia. And Ethiopia, like many tropical countries, has problems from malaria. And one of the best treatments for malaria at the moment is this molecule here called artemisinin, which comes from a plant called Artemisia that grows in China. So quite early on in our collaboration with Ethiopia, we looked at the African Artemisia to see whether we could extract out artemisinin, which didn't work very well. But now we're looking at using singlet oxygen to try and make analogues of artemisinin, which contain this, you can see it has two oxygens with a bridge and another oxygen here, so-called trioxane group. And you can make the same trioxane group using singlet oxygen, particularly the work of the German chemist Griesbach. And we've looked at seeing whether we could make these materials in supercritical CO2. And this again was Jess Hall's work. And it does work, and you can see here's the first amount we made with continuous reaction. And so we have the idea that in Ethiopia, people could make anti-malarial drugs with supercritical CO2 because CO2 is easily available even in Ethiopia from fermentation using the energy of the sun for the photochemistry. Whether you would directly shine the light on the tube or have photocells and use the photocells to power the light is a question of engineering, but the principle is quite exciting. My colleague Mike George has a vision of a mobile anti-malarial factory that would drive round. I think this may be a little far in the future, but it's something that's well worth going for. So